Now, I've given you 3 more practice problems to do. And these are more challenging. These are more challenging because, as you see, I have not completed the reaction for you. So what you need to do is, given only these reagents, you need to predict the products, write their correct formulas, and then balance the equations. Don't worry about the state indicators right now. It will be a big help to you if you can identify which reaction type you're working with. Because if you can tell that it's an acid-base neutralization, then you know that you'll be generating water as a product. If you know that it's a single replacement reaction, then that will give you clues as to your products, and so forth. So I would like for you to pause the video and see if you can complete and then balance these 3 equations. Identify the reaction type first if you can, and then go ahead and do that. So pause the video and give that a shot. And when you're done, continue the video and then I'll walk us through them. Okay, pause the video now. All right, let's take a look at the first one here. Trying to figure out which type of the reaction it is. And I can see right away that I've got an OH there. This is sodium hydroxide. And I have an acid. This is phosphoric acid. So I've got a base and an acid. This is going to be an acid-base neutralization. And acid-base neutralization are special kinds of double replacement reactions where the cation of the base is going to switch places with the hydrogen of the acid. So if that happens, then the sodium is now going to go with the phosphate. Sodium is a +1. Phosphate is a -3. So I need 3 of these sodiums to balance it. Sodium phosphate. And for now, we're not going to worry about the state indicators. What's the other product? Do you remember? It's water, isn't it? Because the hydrogen of the acid is going to pair up with the hydroxide of the base, and we're going to get H2O, but I'm going to write it this way for now because it's going to help me balance the equation. All right, we know that this is really H2O, right? But I'm just going to write it that way for now to help me balance it. So here we go. We're going to balance it. I've got 1 sodium, 3 sodiums. So I need 3 sodiums. I have 3 hydroxides from the base and only 1 OH in the water that came from the base. So I need 3 of them. So 3 hydroxides, 3 OHs in water from the base. 3 sodiums, 3 sodiums, 3 hydroxides, 3 OHs in water from the base. 3 hydrogens from the acid, 3 hydrogens from the acid. 1 phosphate, 1 phosphate. And it's balanced. Moving on. This looks like I have a standalone element reacting with a compound. Now remember I said that combination and decomposition reactions are not predictable, so we're going to assume that this is not one of those. Well, it's definitely not a combustion reaction. I don't have a hydrocarbon reacting with oxygen. It's definitely not an acid-base reaction. I do have an acid here, but this does not look like a base. This does not have hydroxide. It's not any of the other bases that we'll see, such as ammonia, and I'll talk more about that later. So this is not an acid-base reaction. This is a standalone element, so it cannot be a double replacement because this is not a compound. so it must be a single replacement. So in a single replacement reaction, a single standalone element is going to come in and kick out some species in the compound to take its place. And then the species that is kicked out will become a species alone by itself. So first of all, when this hydrogen becomes alone by itself, well, hydrogen is a diatomic molecule when it's in its elemental state. So we've got to remember our diatomic molecules. So when this leaves the compound, it has to form H2 to become a diatomic hydrogen gas. Now the aluminum is going to pair up with the chloride. Aluminum and chloride. Aluminum is +3, it's fixed at +3 as an ion. Chloride is a -1. So how many of these chlorides am I going to have? To balance out with that +3 charge, I need 3 of these chlorides. So that's the correct formula for aluminum chloride. So I have the correct formulas for my products. Now that I have the correct formulas, I can balance the equation. And we're going to run into a little bit of a snag here. I know it's coming up, but this may be the first time that you've seen it. So I'm going to use a pencil for this because I'm going to have to erase my work halfway through this, and I'll show why. We're going to balance our equation here. We've got 1 aluminum, 1 aluminum, 1 hydrogen, 2 hydrogens. So I'm going to put a 2 there. 2 hydrogens, 2 hydrogens. Go back and confirm that everything's still good. 1 aluminum, 1 aluminum. 2 hydrogens, 2 hydrogens. 2 chlorines on the reagent side, 3 chlorines on the product side. Now this is the problem that I was telling you about. This is why we're having to use a pencil on this one. On the reagent side, I have an even number of chlorines. On the product side, I have an odd number of chlorines. So there is no coefficient that I could just put there and make the number of chlorines here equal the number of chlorines there. In this case, both of these coefficients are going to have to change. And what is going to tell us how to change them? We're going to have to determine the least common multiple. The least common multiple of 2 chlorines and 3 chlorines is 2 times 3, which is 6. So we are going to need to adjust these coefficients here and here so that we can get 6 chlorines on each side of the equation. How do I get 6 chlorines here? Well, that 2 needs to go away, and I need to replace it with a 6. So I'm going to do that. Okay. How do I get 6 chlorines over here on the right side? I can put a 2 coefficient there. So now I have 6 chlorines and 6 chlorines. Let's just make sure that I didn't mess up anything. 1 aluminum, 2 aluminums. Aha! I did mess up something. I need to fix that. 2 aluminums. 2 aluminums, 2 aluminums, 6 hydrogens. Ah, now the hydrogens have to be fixed. 6 hydrogens. 2 aluminums, 2 aluminums, 6 hydrogens, 6 hydrogens, 6 chlorines, 6 chlorines, and it is now balanced. So that's an example of one of those cases where I might have had to erase a coefficient that I'd already written and then write new coefficients based on least common multiple math. All right, moving on. We've got one more equation to do, and this looks an awful lot like a combustion reaction. I have a hydrocarbon reacting with oxygen, and so almost certainly this is a combustion reaction. And we know in our combustion reactions I generate H2O and CO2, hot water and carbon dioxide. So here we go. I'm going to balance my equation now that I have my correct formulas. I have 2 carbons. I need 2 carbons here. 6 hydrogens. There we go. Now I've got 6 hydrogens. Excellent. Now I've got 2 oxygens here on the reagent side. How many oxygens? Count up how many oxygens I have on the product side. Looks like I've got 3 here and 4 more here. So 3 and 4 makes 7 oxygens over here and 2 oxygens over here. Now this is a bit of a challenge because I have another situation where I can't just change one coefficient and have everything balanced. If I have 7 over here and only 2 here, there is no whole number that I could put right here to make everything balance. If I put a 3 here, it makes this 6, and that's too few. If I put a 4 here, it makes this 8, and that's too many. So somewhere between a 3 and a 4 would be perfect. But I'm not allowed to have fractional numbers or decimal numbers as coefficients. So what do we do in this case? Well, let's be mathematical about it and figure out what is the correct number that should go here if I were not limited to just whole numbers. If I could pick any number to go here and make it balance out with 7 oxygens, I could put a 3.5 here, couldn't I? 3.5 times 2 is 7 oxygens. And now everything's balanced. But as you know, we can't leave a decimal or a fraction coefficient. But the equation is balanced. It has the same number of each atom on the reagent side as it does on the product side. But we've got to fix that decimal coefficient. So the way that we do that is we're going to multiply this coefficient by 2. So it becomes a 7. Well, this is an equation. And in equations, whatever you do to one thing, you have to do to everything to keep everything balanced. So if we have to multiply this by 2, we're going to multiply all of these coefficients by 2. So this 1 becomes a 2. This 3.5 becomes a 7. This 3 becomes a 6. And this 2 becomes a 4. Okay? So now let's just confirm that it is indeed balanced. 2 times 2 is 4 carbons here. 4 carbons here. 2 times 6 is 12 hydrogens here. 6 times 2 is 12 hydrogens here. 7 times 2 is 14 oxygens on the reagent side, 14. And here I have 6. And 4 times 2 is 8 more. So 6 and 8 is 14 oxygens on the product side. So it is balanced. Coefficients here are 2, 7, 6, and 4. And of course, this is probably going to be a gas. And this will be a gas. And just so that you have it in your notes, even though you might not know this yet, but this is soluble, so I would give it an aqueous state indicator. But again, we'll be getting to that later. So there you go. Some practice for us to balance chemical reactions, identify the reaction types. I've shown you a few little tricks to help you balance acid-base reactions by writing the water molecule like this so that we can balance the hydrogens and the OHs separately. I've shown you how to use least common multiple math to resolve some tricky balancing. And in combustion reactions, I've shown you how to use temporarily a decimal coefficient to balance everything numerically, and then multiply everything by 2 to get rid of the decimal.